Previous videos discussed how to get clean signals from a Bourne's rotary encoder. If you've worked with this device, you'll know it can be tricky. This video will pull together all the details, software, problems, and solutions. It features a PCB designed to make using the encoder simple and reliable. If you like the content here, please consider subscribing to my channel and leave some helpful comments. Thanks for watching. Here's a shot of the Rotary Encoder PCB. Just turning the dial here counterclockwise and clockwise. So the PCB solder side is what's shown, and the Bourne's rotary encoder mounts there. So this way you'll get a mounting with the barrel and all the components will be clear. The other side of this board looks like this. It's got all the components on it, and if you mount this in a panel, then all these components will then face away and they'll be easily accessible. But that's pretty much how this is set up. It's pretty simple. We're driving a New Haven serial display, which is communicated to via an SPI interface. So we reset this and we turn clockwise, and then we turn counterclockwise. And actually you'll notice the rotation is backwards, and there's a reason for that, and we'll get into that a little bit later in this video. But for the moment, let's just see how this works. So we'll go back and forth really fast here, and we're incrementing here in the clockwise direction, and we're decrementing in the counterclockwise direction. Now you'll notice there's a SEL equals 0. That's your push to select. So that's 0 and 1. And there's a digit that's just to the right of that that's blinking. And that digit is the past B variable in the interrupt service routine. And you'll notice it's kind of winking a little bit. And it actually should be staying at 1, but it isn't. And like I said, we'll get into that a little bit later in the video, but one of the switches in the encoder is a little tentative, and there's actually a simple solution to that, but this is kind of good that this has happened because it illustrates this problem. So if I reset this and I turn clockwise now it's working correctly. And if I go counterclockwise, it's working correctly. Back to clockwise, back counterclockwise again. So that's what this does. It's pretty straightforward, and I'll get into the example C code that makes this run. Here's the scope signals. The top trace is int 0 and the bottom trace is int 1, and these are actually idling at 5 volts or VCC. So we'll go ahead here and we'll operate this dial. And every time this dial finds a detent, these two signals should both idle at 5 volts. But you'll notice on the top trace, if I play around with this a little bit, there we go. There we go. So we're at a detent, and the int 0 signal is at logic 0. It should be back up at VCC. So if I twitch this dial a little bit, there it comes back. So this is a little bit of a problem. It has to do with the mechanical switch mechanism in the dial. It's not perfect, and there's actually a simple way around it, and we'll discuss that a little bit later. Luckily, it only happens on one of the switches. The int 1 signal behaves properly, but it's the int 0 signal that's a little finicky. And we'll just look at that again. It's kind of random. There we go. So we'll discover how we can correct this problem, or basically ignore it and make the dial increment and decrement reliably. Let's take a look at the Quadrature Encoder Signals. And A and B are what are on the terminals of the encoder, and they're arbitrary, so A and B really could be B or A here, it doesn't really matter. Same with the directions, counterclockwise shown here on top, clockwise shown on the bottom. These could be reversed as well. It's the phase of this set of signals that creates the quadrature structure, and if we go from here to here, we've got 360 degrees, and these two signals are offset by 90 degrees, or 1/4 of a full cycle, and hence that's the term quadrature. So we've got logic 1 here indicated as off on the switch because we got pull-up resistors in the circuit. We'll take a look at that a little bit later. And then on, which is when the switch closes and pulls the signal down to logic 0 or ground. So this line here, these dotted lines, represent the detents in the encoder, and this one has 24 detents in a complete revolution. So the active part of the signal actually occurs between the detents. So you can see here, each detent, both signals idle at VCC, which mean the switches should be open. And we saw earlier in the video that that switch is a little finicky, and that actually isn't always the case, but let's assume in a perfect world it is, and we'll move through how this works. So starting here at a detent and moving clockwise, the first event is the A signal drops to 0, followed by the B signal dropping to 0, followed by the A signal going high, then followed by the B signal going high. So if we go over here at this detent and we move in this direction, you'll see here that the exact opposite happens. The B signal goes low, followed by the A signal going low, followed by the B signal going high, followed by the A signal going high. Again reaching this detent, and both signals now idling at VCC. So the trick with this is to feed these signals into 2 interrupt service routines and do some logic to track direction and create an increment in one direction and a decrement in the other direction. We'll see how that's done a little bit later in the video. So that's kind of how this works with the quadrature signals, in case you didn't understand that. So let's take a look at the circuit diagram and see how this encoder is actually processed and cleaned up and allowed to generate these clean signals. Here's the schematic for the Bourne's Rotary Encoder PCB. There's a set of dry contacts right here labeled W and S on the switch, and it's basically your push to select. They're normally open, and they just run out to this terminal block here, J2. They're open, and then when you push on the dial, then these contacts close momentarily. The quadrature signal is generated here, terminals A, C, and B. They're normally open when the switch is positioned at a detent, and earlier in the video we saw that there's a mechanical problem with this switch, and sometimes one of these switches will not open. We'll get into how to fix that, deal with that a little bit later. But these switches share a common center terminal here, which is grounded, and they're normally open, and that's how they work. Bourne's recommends this filter circuit, which is the 4 10K resistors and 2 capacitors. Their circuit suggests 0.01, and I found that doesn't work very well, so that's why you're seeing 0.1 microfarad. The 10K resistors are fine, and what they do is they pull up the signals here, so when the switch is at a detent and these two are open, the signals idle at 5 volts or VCC. So they just feed a Schmidt trigger with hysteresis on the inputs, and this is an inverting Schmidt trigger. So I just connected 2 blocks here in series, so the input and the output are the same logic sense, and then I paralleled two of them together to give a little bit more drive capacity, and they just run out to your int 0 and int 1 terminals, and they give nice clean signals with good rise time. This has been tested with 4 feet of shielded cable specified down here, and it works pretty well. So the other thing that you want to keep in the back of your mind is on your MCU, if you're running 5-volt logic, you want to use this 74HC14 chip, which is a 5-volt chip. Power this with 5 volts so you don't exceed the input capacity of the processor pins on your MCU. If you need to run at a higher voltage, you can substitute a CD40106BE and you can run this at a higher voltage, but exercise caution to make sure that your voltages coming out of this PCB don't exceed the inputs on your MCU. So that's pretty much how the circuit operates. It's pretty simple, pretty straightforward. There's a bypass capacitor here on the input just as a cautionary measure to filter out any noise that might creep in here. But this circuit works pretty well, and it should generate nice clean signals. Here's a sample C program. There's a link in the description to get this program. This is just shell code, just plain vanilla C, and it's quite well commented, and it goes through the deep dive on each state of the encoder and what happens to the variables. So it's pretty helpful. You can adapt this to any platform that you want. The only thing that's really required here is you need to have 2 interrupts on your MCU, and you need to be able to configure one of those interrupts to detect a level change and the other interrupt to detect a rising edge change. So what I did with my project is I was working with the Arduino Nano V3, and I kind of like working at the register level, so I created these macros that are used to program int 0 and int 1. You can use these if you're on that same platform, but these can be modified as needed, or you can use library functions that accomplish the same thing. So just keep that in the back of your mind if you're going to use this code. Let's take a look at these events. So the int 0 output on the PCB is connected to the int 0 interrupt input in this example, and we just go ahead and take a look at the signals here, and as we saw in the graphic, clockwise int 0 goes low, then int 1 goes low, int 0 goes high, int 1 goes high. So that's what happens when we turn this clockwise. And we also have an initial state that we have to take under consideration, and that's what we call this past B variable. So if we come down a little bit further in the code, here's the 2 interrupt service routines. One of them toggles the past B, 0, 1, 1, 0, 0, 1, and so forth. And the other one uses a ternary operation to either add or increment what I call here my menu select variable, or decrement it depending on the value of past B. So this is pretty simple, and what's happening here is the signal that processes the past B variable should be the level change interrupt, and the signal that processes the increment should be the rising edge triggered interrupt. These numbers don't really matter, and we saw earlier that encoder, one of the signals, which was int 0, is a little finicky. So I found through testing that if you have an encoder that has a finicky signal, avoid putting that signal on the interrupt service routine that manages this past B variable. So in my example, the int 0 signal was the one that was funky. So what I would do here is I would change these numbers. Int 0 becomes int 1, and then int 1 becomes int 0, and make sure that you change the triggering down here so that what happens is this particular logic here is always triggered as a level change. So if we make this int 1, then down here we've got to say int 1 CHG, or level change. So that's how you can get around that little anomaly with the encoder. And if the signal that drives this interrupt is a little tentative, it really doesn't matter. This is the one that creates kind of a spontaneous change in the sense of clockwise and counterclockwise, and you'll be using the encoder, and all of a sudden you'll find out that clockwise doesn't increment anymore, but now decrements. It's kind of spontaneous. So the variables that you'll want to use in your application would be your menu select. Every time that encoder passes through a detent, it will, or from detent to detent, it'll increment or decrement this value. This variable here, its initial conditions determine whether clockwise increments or clockwise decrements, so you want to set that up right. And then this is just a direction flag, and the way this program is set up, that direction flag, if it's 0, we're turning clockwise. If it's 0 here, we're turning counterclockwise, and that's based on how past B is set. So just a heads up, if you go ahead and reverse these two signals to account for a finicky switch, then the logic here is also going to be inverted from what's shown here. So that's pretty much it. And down a little further, here's your main program. You can put any application code in you want. Make sure that you have your interrupts triggering properly, and that you turn on the interrupts, that you turn on your global interrupts and nothing's masked. But this code again is linked in the description. You can pull this program up and feel free to modify it and use it as your application dictates, and the comments here explain everything. So hopefully that should be helpful. We've just covered a lot of ground and details. I hope the video has been informative and helpful. This project took more time to figure out than I had anticipated. Several circuits and software attempts failed to yield reliable results. The one presented here was finally successful. To help with all the details, please see the links in the description that provide an example well-commented C source code with interrupt service routines and application variables, a quadrature signal diagram, an encoder PCB manual, which includes a complete explanation of this project, parts lists, and how to get a bare PCB if you need one, and a circuit diagram.